I do if I want to go to the bathroom?
Yeah, you go to the bathroom.
You just
Okay.
crawl.
Now,
Said.
refraction.
Hey, what is fun?
Okay. Now, we've talked about reflection, which is light bouncing off reflective surfaces. So a surface that is capable of, it doesn't absorb light, it actually bounces off light at the same frequencies that it comes in. Now, refraction is slightly different. When we say refraction, you need to think in terms of light being bent. Okay? And so we have these key learning intentions. Light speed, you know, is 300 million metres per second. But light speed varies in different mediums. So when light is travelling in a vacuum, it's 300 million metres per second. When it travels through air, air is not very dense. And so it's pretty much moving at the same speed, 300 million metres per second. But when you put it into water, the water slows it down. When you put it into glass, it slows it down. You put it into diamond, it really slows it down. Okay? And because the denser the medium, the more it is slowed down. And when light hits these medium at an angle, it will bend. Okay? And we'll try and explain that as best we can. Okay, this is revision, although I did put some gaps just to get you to fill things in. You know the electromagnetic spectrum now. You know all of these wavelengths are types of light. So be clear, radio waves or radio signals are light and they travel at light speed. Okay. The trick question in tests and exams is we will see if we can confuse students between sound waves and light waves by talking about radio signals. And when you hear the word radio, you start thinking about music that you listen to, and you say sound wave, and it's not. Radio signals are forms of light. Okay? Microwave, infrared, visible, ultraviolet, X-ray, gamma ray, all forms of light, just with different frequencies and different amounts of energy. That's what we're talking about here. You have a long wavelength, you have low energy. Short wavelength is high energy. Now, they all travel at light speed, which is about 300 million metres per second in a vacuum. But what if you're not in a vacuum? Can I change? Yep.
What's a vacuum?
No atoms. So between the sun and the earth, there's effectively no atoms in deep space. There's a few. There's a couple. There's maybe one helium or one hydrogen atom per cubic metre. It's not much. Okay. Now, the speed with which light moves through transparent substances depends on how dense those substances are. And that density, another word for the density, how thick something is if you like, is the refractive index. Okay? And that is a measure of how much light is slowed down. How many times slower light moves through a transparent substance? Now, these numbers down here in our diagram are this is actually 300 times 1,000 kilometres an hour, or 300 million metres per second. This is just that value. And moving through air has a refractive index of 1. What's 300 million divided by 1? 300 million. Because the 300 million is light speed. That's light speed. So 300 million divided by 1 equals 300 million. What's 300 million divided by 1.33, which is the refractive index of water? The answer is actually 225 million is the answer. You can put it in a calculator, you'll get that. And that means light moving through water is only moving at 225 million metres per second. So it has been slowed down. You put it in perspex, this clear plastic, and it slows down to 201, give or take, million metres per second. Glass slows down even more. Diamond is about, as high a refractive index as you can get, because light has to pass through, remember, and you're moving at less than half speed, 124 million metres per second. So that is light moving through different substances. And because light speed changes in different substances, light will bend when it comes in. Yes?
Would you notice it for like diamond with that? If you're showing something,
you can measure it.
Would you like to see it go in and then stop?
If you could, remember your brain, you can think at 150 metres per second, the electrical signals in your brain. So when you, like, have you ever seen, what's it called? I think it's called a frogfish, which is the world's fastest predator animal. It can unhinge its jaws, grab something and fold itself back in 0.06 seconds. So you actually can't see it move. Like, even if you're filming it, it's too fast. It's going between the film frames. You have to be using a very high-speed camera. So just for a frogfish, you would be looking at it and another fish would come in and all of a sudden it's gone. And there'd be, the water would swirl and be a bit of dust kicked up, but you go, I literally can't see that, let alone something like this.
What if you put on sonar?
That's not going to matter. You have to have a camera with a high-speed camera using more than 24 frames per second to catch something like that. But it is detected. It is measurable, and in fact, it's not only measurable. You can measure it in this classroom. Like, we get the light boxes out, we do some simple mathematics, and you go, oh wow, yeah, like the amount of bending, the amount that light bends is proportional to how dense the substance is. So if I measure the angles, I can do the math backwards, and I can work out how much light is slowed down. So, and we'll do that out there. Ooh, I made that. No need to clap. Okay. Thank you. Well done. This is, we'll say, air. And what is light speed in air?
300 million.
We'll say 300. We're not, no trick questions here.
300
Meters.
million.
Oh, 300 million
Eyes.
meters per second. Now, this block of clear plastic here is perspex, and that is, the light is being slowed down as it hits that block of perspex. Now, it's hitting straight on, so there's no bending occurring at all. That's one of the rules of this game. If it comes in straight, it goes out straight. No bending at all. But the refractive index, because of this refractive index of purple, we get this slowing down effect. And then when light moves back into air, it goes back to 300 million meters per second, because it's now no longer interacting with, it doesn't have the density of atoms or of matter that was causing this slowdown effect. So the wave just continues to propagate 300 million meters per second. Let's see, light travels faster in a vacuum, slower in air, slower again in liquids, and slowest in solids, e.g. glass. If light enters another substance head-on, it won't bend. That's a key idea. It's a bit of a, not a trick question, but one of the questions we use to see if people are paying attention. Like we'll say, well, if I shine my torch through a thick glass block, estimate how much the light will bend. And you go, well, if you're doing it straight on, it won't bend. It'll just go straight through. Okay. Now, so let's see if I can think of. No, I thought I had a good example for you in terms of looking through glass when it's light bright. You've got lights on inside and it's dark outside, but no, that's something else. Okay, I'll change. Okay, now this is an angle. Okay, so refraction, change in direction of any wave as it passes on an angle. It's got to be on an angle on a boundary of media of different densities. Air, that's high density. Oh, sorry, that is high wavelength. That's air. Put that there. Put just air here. Put water here. Now, is water denser than air? Yes, it is. So bending occurs. If it was going from air to another gas exactly like air, no bending would occur at all. But yeah, it's air going into water, so bending occurs. Now, what we have is the incident ray. This is the incident ray coming in. When it enters that substance, this is the norm over here, and this is the refracted ray, or the ray going through the substance. And that's what's happening there. So what we have here, this is the angle of incidence, and we'll say maybe it's 40 degrees, and the angle of refraction is maybe 30 degrees. So please note that the angle, again, like for mirrors, is the angle between the norm and the incident ray, the incident ray going in and the refracted ray going through. Okay, So that's what, put those numbers in for sure, 40%, 40 degrees, 30 degrees, because it's bending towards the norm.
It's too
And the
dark.
opposite is true. Huh?
It's too dark. Like the actual thing on
Yeah,
the...
it's black.
Oh,
It's
so
not,
it's
it's black and white, so you won't be
it's
able
not
to see it.
printed out well.
It's false. It's just...
Oh, well, just use arrows, or draw it below, or do it on this one.
Deal with it.
You've got a second one here. Worked out okay. Just do the same thing. In fact, I've already got incident ray and refracted ray here. So you can fill in some numbers and put in angle of incidence, which is already there, and angle of refraction. So that second diagram will help you out anyway. So just fill in some numbers. So it bends towards the norm. Now, did anyone, when you were at the pool last Friday, and maybe someone was doing the volleyball or something like that, and you were standing on the edge of the pool, looking at the people playing, and did anyone see, oh wow, everyone's legs look really short? Like, have you ever seen that when someone's standing in the pool and their legs look very short but fat?
yes.
Yeah? And you go, well, that's kind of
Oh,
weird.
that's all right.
Yeah? And that's what's happening here.
You need to be more appropriate now.
Okay. That's what's, can I change?
Yes, you can.
Oh, now, really important, I forgot to mention this key idea. Let's look at this wave coming in. Okay, so everything, the whole wave front is moving at light speed, yes? The whole wave front is moving at light speed. Now what happens when the leading edge hits here?
It goes slower.
It goes slower.
It feels small.
And then the next part hits and goes slower, and the next part hits and goes slower, and the next part hits and goes slower. And because of that, this wave front, you'll see it actually, this is the angle coming in here, this is the angle going there. It actually gets bent along that wave front. It's like if waves were coming in, if you had an ocean wall and waves were coming in on an angle and they were hitting on that ocean wall and they'd get straightened out in the direction of the ocean wall. And that's kind of what's happening here. That gets slowed down, so it heads off at that direction and so on, and the whole wave front ends up being bent more towards the norm. Okay, and the reverse is true also. Let's have a look on the next slide. There is our second example, okay, where okay, so we have, that's what we've just seen, incident ray, refracted ray, angle of incidence, angle of refraction. Again, if this was 40 degrees, we'd say this is 30 degrees. But let's have a look when we have, this is now up here, this is water, and this is air. And what happens when you go from dense into less dense? It bends away from the norm, and that's what's happening up here. So if this was, would say 35 degrees, I'm just choosing a different number, and we would say maybe this will be 45 degrees coming out. The way it actually works, if you want to draw it as a single block, which is not a bad way to go, there's the norm, come in, that's 40 degrees, that's the norm, we'd say that is 30 degrees, and then, that's not very distinct, I might make that a bit more obvious, there you go, and then when it comes out the other side, there's a new norm, and that will be 40 degrees again, okay? And so that line there and that line there will be parallel, but they're going to be offset by a little bit, okay? So come in at 40, bend 30, come in at 40, I'll send you out. Don't distract other people, okay? So that's how you can do that on one diagram, or you can have it over the two diagrams here. So when you go from less dense to more dense, you bend towards the norm. When you go from more dense to less dense, you bend away from the norm. Okay. Now, finally, okay, there's a little bit on a prism, and we've seen similar things like this before. When light enters a prism and it's coming in at an angle, so it's coming in at an angle and it's being bent towards the norm because the prism is denser, but red wavelengths of light they actually bend less than do orange, yellow, green, blue, indigo, or violet. They all bend different amounts because of their different amounts of energy, and so that white light coming in is split into the colours of the rainbow, Roy G. Biv. So is red light higher energy than violet light, or is it the other way around?
The other way around. I think it's the other way around.
Yeah, it's the other way around. This is red wavelengths. You can see they're actually longer. So they've got low frequency, low energy, high frequency, high energy, and because of that difference, it splits that light out into the different colours. Okay. And that's why you see rainbows because the raindrops themselves are both reflecting light internally and refracting light on angles, and so it goes and just splits it all out. And there's your Roy G. Biv again. Now, I think I have one more. Yes. How to kill things on camp. You're going on the Year 9 camp, you're going to the city, so you won't get to spear fish or anything like that. Okay. Now, this is apparent depth, and you may have seen this effect at the pool because of the refractive ability of water. And so people look shorter in water. And in terms of this man fishing here, your eye is programmed to assume that light only moves in straight lines. Yeah? That's the way your eyes work, your brain works. It just assumes, because light does just move in straight lines in almost every experience you have as an evolved organism, except in these situations. So when you look at the fish in the water, you see the fish as being at the apparent position because you assume that it's a straight line. But the fish is actually a little bit forward and further down, yeah? And so the classic scenario, if you've maybe seen a survival show on TV or something, is I'll say you can't aim for where you see the fish because you'll miss. If you're trying to shoot it with a bow, you'll just miss. You have to aim in front of it, a little bit below, and you'll be okay. Okay? If you put your hand in the water, you'll still miss. Okay? Now we're going to watch an amazing video of a fish eating a bird. Not a bird eating a fish, pretty common, but a fish that actually hunts birds. So it comes from underwater and jumps up, and it has the reverse problem to do, and it does that for a bird that's moving pretty fast.
Do we have to
And
watch this?
huh?
Do we have to watch
Yes.
this?
Well, you can close your eyes if you're so inclined. But
You know,
and because I like you, there you go. That's the entire slideshow on one slide. Put a big C for cram card. Put a big pink box around the entire thing if you like. But that pretty much covers everything that we've discussed today. Okay? Okay, what refraction is. Light moves in transverse waves, you know this. Light speed is 300 million metres per second. It decreases in denser medium. Refractive index is how much light is slowed down compared to a vacuum. Refraction doesn't occur if light hits straight on. See, here's a wavefront. Gets slowed down, but it doesn't bend at all. Come in at an angle, bend towards the norm. Go out at an angle, bend away from the norm. So if you want to put at this point here towards norm and here away from norm, that would be about the only information you need to provide on that slide, and that would be it.